Hi there. Welcome to Chapter 6 of your textbook. Chapter 6 is about normalization of database tables. Now, normalization is an important concept, so pay attention in this chapter as the concepts that you learn here will be useful to you when you are out there designing databases. So imagine we have this table and we are storing different attributes in this table, and we want to create a database to manage this data better. Now, when you look at the different types of data that are stored in this table, you can kind of recognize that we have data on projects. So we have the project number, project name. We have data on employees, employee number, employee name. We have data on jobs, right? And things like charge hour, meaning charge per hour, and hours billed, right? So intuitively, we can kind of understand the entities that would emerge from this data. Well, normalization formalizes this process, right? Normalization is a process that assigns attributes to entities so that data redundancies are reduced or eliminated. So in this chapter, we'll explain normalization and its role in the database design process. We'll describe the different normal forms. We have the first normal form, second normal form, third normal form, and the fourth normal form. We also have something called the Boyce Codd normal form. Now, we won't be going much into the Boyce Codd and the fourth normal form. They're not used very often, and given the short nature of this course, it's best that we stick to the first three normal forms and learn them properly. Okay, so we'll see how normalization rules can be applied to create and correct table structures. We'll also identify some situations that require denormalization to generate information efficiently. Okay. So normalization is the process of assigning attributes to tables based on determination in order to minimize data redundancy. So normalization helps to evaluate and correct table structures and reduce data anomalies. There are different normal forms. Now, the way the terminology works, the second normal form encompasses the first normal form and then adds a few criteria. Similarly, the third normal form encompasses the second normal form with some additional criteria. So you can think of this as concentric circles, the most basic normal form being the first normal form. The second normal form encompasses all the conditions and the criteria of the first normal form and adds a few of its own criteria. So then you get the second normal form, and then you get the third normal form. So the third normal form encompasses the second normal form, which encompasses the first. The process of going from the first normal form to the second, from the second to the third, is called normalization. The process of reversing, the reverse process of going from the third normal form to the second normal form, or from the second to the first, is called denormalization. Okay. Now we'll see when do we need to denormalize a table, and we'll see why that's done later in the chapter. So as we were discussing, higher normal forms are better than lower normal forms, meaning the second normal form is better than the first, the third better than the second. Right? There is also denormalization. Now, denormalization generally produces greater data redundancy. However, it also comes often with increased performance. Okay. So, normalization is used when you are designing a new database structure. And normalization analyzes the relationship among the attributes within each entity. So if you recall back to the idea of entities, entities are nothing but tables that we have in the database. Each entity has certain attributes. These are the columns that are there in each entity. Normalization analyzes the relationship among these attributes. So we're talking about relationship between the attributes of an entity. And we'll see this will become more clear when we are going through an actual example. Normalization determines if the structure can be improved through normalization, right? And this is just the process of normalization. And it improves the existing data structure and creates an appropriate database design. The objective here is to create something called well-formed relations. Now, relations, by relations we mean tables, right? Now, what are well-formed relations? Well, here are the characteristics of a well-formed relation. Each table represents a single subject, right? So in other words, each table in the database logically represents a single subject, right? Each row or column intersection contains one and only one value and not a group of values, right? So when we look at the data in the table, each cell in that table should contain one and only one value, not a comma separated list of values or multiple data types. No, just one and only one value. No data item will be unnecessarily stored in more than one table. In other words, the storage of data should be efficient. No data item should be stored in more than one table. Right? So no redundancy, right? There sometimes is a necessity to store an item in more than one table, the same item in more than one table, and that's generally done for performance reasons. And so therefore you see this use of the word unnecessarily stored, right? Sometimes it is necessary to store the same data item in multiple tables. All non-prime attributes in the table are dependent on the primary key. What do we mean by non-prime attributes? So think back to the employee table that we were looking at in other chapters. The employee table has the primary key employee number. Employee number is a prime attribute. All other attributes in the employee table are non-prime attributes. So one of the conditions of a well-formed relation is that all non-prime attributes are dependent on the primary key. In other words, things like employee first name, last name, date of birth, etc. can be determined by the employee number. If you know the employee number, then you can identify that employee and determine their non-prime attributes. Okay. Each table has no insertion, update, or deletion anomalies. Now, what are anomalies? We'll get into this and we'll look at one example of insertion, update, and deletion anomaly each. Okay. So when we go through the normalization process, the example we're going to be using is this particular data set that we have. Okay. So the normalization process ensures that all tables are at least in the third normal form. Okay. Higher forms like BCNF or the fourth normal form are likely not to be encountered in the business environment. The process works one relation at a time. Again, by relation we mean table. So it works at one relation at a time. It identifies the dependencies of a relation and progressively breaks the relation up into a new set of relations. An example here would be there are several entities present in this particular table. We have projects, employees, we have jobs, we have the hours billed, and so on, right? So we have about 2 or 3 entities here. Normalization will break this up, as the slide says. It identifies the dependencies and then progressively breaks the relation up into a new set of relations. Okay. So this table here basically gives you the characteristics of each normal form. The first normal form, the defining characteristic of the first normal form is that data is in a table format. There are no repeating groups and the primary key has been identified. The second normal form, the defining characteristic of the second normal form is that all tables are in first normal form, and an additional criteria, no partial dependencies exist. Now we look at what are repeating groups and what are partial dependencies in subsequent slides. The defining characteristic for the third normal form is that the table should be in second normal form, and the additional criteria that no transitive dependencies exist. Again, we'll understand what are transitive dependencies through an example. The Boyce Codd normal form is a special case of the third normal form where every determinant is a candidate key. Now you don't need to particularly understand what exactly this means, since we're not going to cover BCNF and 4NF in this lecture. So let's look at this data set that we have, and let's see how we can convert this table into first normal form, right? So what we're going to do is we're going to operate with this data set. We're going to convert it to 1NF, then we're going to convert it to 2NF, and then to 3NF. Okay. So notice that there are several problems with this data set. Like storing this in a database is not feasible. Why? Well, first recognize that there are multiple values in a cell. And as we know, well-formed relations or well-formed tables should have only one value in each cell. Right? All the tables that we have looked at so far in previous chapters, they are well-formed relations. Right? Each of them, each cell of each table contains one and only one value, right? Not multiple values. For example, here, employee number contains a list of values. Employee name contains a list of employees. Job class contains a list of jobs, and so on. Right? So this structure is not really in any normal form at the moment. And that's what this bullet point here is saying. Note that each single project number, each single project number can reference a group of related data in the employee number, employee name, job classification, and charge per hour columns. Right, so project number 15 references a group of data, right? Several employee numbers, several employee names, job classes, charge per hour, and so on, right? For example, the Evergreen project contains 5 values for each of these attributes at this point. Right? So this data, this relation or table is not in even the first normal form. Now the first step to converting, step 1 of converting into the first normal form is eliminate repeating groups. What are repeating groups? They are exactly what we discussed here. Storing multiple values in a single cell. This is called repeating groups. Okay. So how do we break this up? Well, one way to break this up is to create several entities. Instead of having one row with project number 15, we break it up into several rows that exist here. Right? So here we see that project 15 can be broken up actually into 5 rows, 5 different rows, right? We have employees 103, 101, 105, 6, and 102. Their names are here, their job classes are here, their charge per hour is here, and their hours billed is here. Right? So we can have 5 rows for project number 15. Similarly, we can have 4 rows for project 18, 5 for 22, and then so on. Okay, that's the first step, is we eliminate the repeating groups. In this table here, you see that every cell contains one and only one value, right? Thus we have eliminated the repeating groups problem. That's step 1 of getting to the first normal form. Okay, here you can see we've broken up the projects, and so repeating groups are eliminated. Step 2. This step makes sense to do, right? This step makes sense. Let's look at step 2. Step 2 is about identifying the primary key. Now, initially, when you look at the data, you might have thought that, oh, project number can be the primary key. But really, when you, after eliminating repeating groups, can you use project number as the primary key? And the clear answer is no, right? Because project number 15, for example, can refer to any one of 5 rows. So project number alone is not a primary key. Well, then what is the primary key for this data, for this table? Well, you'll soon understand that project number and employee number, the combination of these 2 fields, can be used as the primary key, right? So you can identify every row in this table if you know the project number and you know the employee number. For example, project 22 has employee 104. If you know that, then you can identify the project name, you can identify the employee name, the job class, charge hour, and hours worked, right? So the primary key for this table is a composite primary key comprising of 2 attributes, project number and employee number. Now, step 3 is we identify all dependencies. Okay. Here we see that on the top are the dependencies that are valid that you want to have. Now, this set of arrows might look confusing, but the way this is going is that both project number and employee number identify all other attributes in the table. So these arrows are actually going like this. Both project number and employee number identify project name. Let me then change the color of the pen. Both project number and employee number identify employee name, right? And similarly, both of these identify job class, charge hour, and hours worked. Okay. So these are on the top of this dependency diagram. So this is called a dependency diagram. The top arrows in this dependency diagram are the ones that are desired, the dependencies that we want, right? They are based on the primary keys. What is the primary key? It is a composite key of two fields, project number and employee number. These two fields identify the rest of the attributes. The arrows on the bottom are less desirable dependencies. So whereas the arrows on the top are desirable dependencies, or in that all the other attributes are dependent on the primary key, the arrows on the bottom are less desirable dependencies, which we will try to eliminate through the normalization process. Okay. So this here, project number to project name, is a partial dependency. So first of all, it is a dependency in that if you know the project number, you can identify the project name, right? Now, it is partial because it is only dependent on a subset of the attributes of the primary key. In other words, our primary key is the composite key comprising of project number and employee number. To determine project name, we only need the project number and not the employee number. So therefore, this is called a partial dependency. Similarly here, employee name, job class, and charge hours are partial dependencies in that they only depend on employee number. We do not need to know the project number in order to identify employee name, job class, and charge per hour. Also note that there is a transitive dependency here between job class and charge per hour, in that job class determines charge per hour. Right? What type of job you do determines how much you can charge per hour. Okay. The reason this is called a transitive dependency is because job class is not a part of the primary key. So again, this is a less desirable dependency that we want to try to eliminate. Again, we want in our database all the non-prime attributes to be dependent on the primary key alone. Okay, so we want to eliminate these partial dependencies and this transitive dependency as well. All right, so this is step 3 of getting to the first normal form, is identify all dependencies. Now you can see that we list a few things below the dependency diagram, right? These are also part of the dependency diagram. So we first list the first normal form, the full relation in the first normal form, and we underline the primary key attributes. In this case, we have two attributes that make up the primary key, so we underline both of them. We then list the partial dependencies, and we identified two partial dependencies. Project number determines project name, and employee number determines employee name, job class, and charge hour. Lastly, we identified the transitive dependency. Job class determines charge hour. Okay. So this is the process of creating a dependency diagram. Now there are different tools that allow you to create these boxes and arrows. Things like Visio, even PowerPoint can be used, or Lucid Chart, right? And on the final exam, you have a question. You'll have a question that asks you to create a dependency diagram. All right, so those are the 3 steps to follow to get to first normal form. Okay, so the first normal form describes the tabular format that conforms to the definition of a relational table in which, number 1, all the key attributes are defined. And in our case, we have defined the key attributes as project number and employee number. There are no repeating groups in the table. In other words, each row-column intersection contains one and only one value, not a set of values. And we saw that earlier. And then all attributes are dependent on the primary key. And we see that here, all attributes are dependent on the primary key. Okay. So that's for first normal form, right? So we got from, just to review, we got from our original data set to the first normal form by following 3 steps. The first step, we eliminated repeating groups by separating out the data, right? Second step, we identified the primary key. So what is the primary key that uniquely identifies each row here? It is the combination of project number and employee number. And third, we identified all dependencies. So we first identified the dependencies that are desirable, and we show them in the top of the dependency diagram. And we identify the non-desirable dependencies as well. These include partial and transitive dependencies. Okay, so in this format, our table or relation is in the first normal form. Now notice that anomalies still exist, right? And we have the 3 kinds of anomalies that still exist in our first normal form. What are they? Let's take a look here. So first of all, we have an update anomaly, right? For example, modifying the job class for employee Annalise Jones requires updating multiple entries. Otherwise, we will get data inconsistencies. What does this refer to? Let's take a look. Here's our data set in first normal form, right? This is in first normal form. Now this here, we are seeing that Annalise Jones has multiple rows here, right? So if the job class for Annalise Jones changes, currently it is listed as applications designer, right? let's say it changes to something else, right? Say design manager or what have you. Then you would have to update it in two places, both here and here. And that's undesirable. Why is that? Because it could very well happen that you update it only in one place, and somehow due to human error you don't update it here. Then Annalise Jones would have two different job classes, and that's a data inconsistency. Right? This problem is called an update anomaly. Okay, and you'll see that our data, even though it is in first normal form here, right, is still suffering from this anomaly. The second anomaly that our data suffers from is an insertion anomaly. Adding a new employee requires the employee to be assigned to a project. Right? If an employee is not yet assigned to a project, then a phantom project must be created to complete the employee data entry. This is a problem because if we want to store data on employees, on all employees, right, in this database, we cannot do that properly, because what if we have employees that do not have a project yet? Keep in mind, project number and employee number are the primary key for this data in the first normal form. We cannot leave project number blank because it's the primary key, right? So if we want to add a new employee, we have to create some sort of a dummy project so that we can store data on that employee, right? That's an insertion anomaly. It's an example of an insertion anomaly. The third anomaly that exists is the deletion anomaly. Suppose that only one employee is associated with a given project. If that employee is deleted, the project information will also be deleted, right? So in here we don't have an example here, but let's say we had project number 26, which was being worked on by only one employee, right? Then if that employee would have to be deleted from the database for whatever reason, then we would have to delete project number 26 as well, right? That's the deletion anomaly. Okay. So how do we get rid of these anomalies? Well, we continue going to a higher normal form. Right now, this table structure is only in first normal form. We continue going through the process of normalization to make it into a second normal form. So let's go through the conversion to second normal form. And it's fairly an easy process. It's again a step-by-step process. The first step is to make new tables to eliminate the partial dependencies. Now, if you remember from the first normal form, we had identified dependencies, and there were two partial dependencies that we had identified. To eliminate these partial dependencies, what we do is we list each of the components of the primary key separately, as well as the composite primary key. So we list first project number, then we list the second component of the primary key, employee number, and then we list the full primary key, project number, employee number. Okay. Each component will become the key in a new table. Okay. In other words, the original table gets now divided into three tables. We will divide this original table This is one table into three different tables. What are the three tables? The three tables are those that are identified by the primary keys that we had listed. The first table will be a project table, identified by the primary key project number. The second table will be an employee table, identified, which uses employee number as the primary key. And the third table will be an assignment table, in which projects and employees, the project number and employee number, will be used as the primary key. Okay, so that's how you eliminate partial dependencies. Okay, always the way to eliminate even the transitive dependency is going to be to create a new table, a separate table. Okay, so then we have the three tables. So now that we have the three tables, what do we do next? Step 2, reassign corresponding dependent attributes to these tables. Dependent attributes are the attributes that are dependent. So in this case, in this partial dependency, project name is the dependent attribute. Similarly, in these dependencies, employee name, job class, and charge hour are the dependent attributes. We assign them to the respective tables that we had created. So you'll see here, project name, the dependent attribute, gets assigned to the project table, and project number is the primary key in the project table. Employee name, job class, and charge hour get assigned to the employee table, and employee number is the primary key here. Similarly, assign hours gets assigned to the assignment table, where project number and employee number are the primary keys. Okay, that's step 2. So you see how we've gone from having one giant table to having 3 smaller tables, right? So this is our second normal form here. We see here we have 3 tables, right? This is the dependency diagram here. We have 3 tables. First table, project, where project number determines project name, and we write it out like this. We underline the primary key, right? The second table is the employee table, where employee number determines the other attributes. Now, we had a transitive dependency that still exists. That still exists in the employee table. Okay? And so that's why this is only in second normal form. We are not at third normal form yet. Okay? All right. So we list the employee table like this, where we identify the primary key and list the dependent attributes. We also list the transitive dependency here. The third table is the assignment table, where both the project number and employee number are the part of the primary key, and together they determine the assignment hours, right? The number of hours that this employee worked on this project. Okay. So that's getting to the second normal form. And so the dependency diagram that we saw, it's repeated here. I've pasted it here. This is in the second, these tables are in the second normal form now. A table is in a second normal form when it is in 1NF and it includes no partial dependencies. So we have, as you'll see in this diagram, we have eliminated all the partial dependencies. That's a requirement for the second normal form for 2NF. Okay, so no attribute is dependent on only a portion of the primary key. All attributes are dependent on the full primary key. Okay. Notice that it is still possible for a table in 2NF to have transitive dependencies, like we have one here. And that's okay. This table, the employee table, is still in 2NF. Okay. To eliminate this dependency, we'll go to 3NF. So let's look at the conversion to 3NF. The conversion to 3NF is very simple. It's a two-step process. Number one, make new tables to eliminate transitive dependencies. So as we discussed, just like we created new tables to eliminate partial dependencies, we can eliminate transitive dependencies by creating new tables as well. In this case, our transitive dependency was between job class and charge hour. So we create a new table with job class as the primary key and charge hour as the dependent attribute. Right? So we create a new table here, call it job, in which the class of job or the type of job that you do determines how much you can charge per hour. Notice that job class, the determining attribute, is still remains in the employee table. In other words, it's not removed from the employee table. We still need it there because employee number determines job class, right? Job class is an attribute of the employee, right? What type of job the person does is the attribute of the employee. So it still remains there. However, we can map these job classes to their charge hours in a separate table called a job table. Okay. So in here, we can underline job class because that's the primary key, right? And so now we have 4 tables. Step 2 was reassigning the corresponding dependent attributes, meaning we move charge hour from employee to the job table because charge hour is the dependent attribute. Okay. So the tables in this dependency diagram are in 3NF. So this is the third normal form, and for all practical purposes, this is the database design that you would implement in your DBMS. Okay. So a table is in third normal form when, first of all, it is in 2NF and it contains no transitive dependencies. Okay. So in here, as you can see, we have no transitive dependencies. Okay, so now let's go through the slides provided by the publisher here just for the sake of completeness, but we've covered these concepts. We've covered the normalization process, right? So from this table, I'd like you to remember what is sort of full functional dependence. The full functional dependence is if attribute B is functionally dependent on a composite key A, but not on any subset of the composite key A, then attribute B is fully functionally dependent on A. Okay. And then you can also say that functional dependence is written this way. We've already seen that. And it is read as project number functionally determines project name. Project number is known as the determinant attribute, and project name is known as the dependent attribute. Okay, so those are the few things you should remember from this slide. Partial dependency, we went through that. Partial dependency happens when the determinant is only part of the primary key, right? Transitive dependency happens when another attribute, an attribute is dependent on another attribute that is not part of the primary key. Okay. Again, if you want to go back and revisit the slides, look at our example, refer to these definitions to understand them. But the reason I went through the example is because it's easier to grasp the definitions once you have been through the example. Okay. Here again, repeating groups. We saw the repeating group problem, right? Where a group of multiple entries can exist for any single key attribute occurrence. The three-step procedure eliminates repeating groups, identify the primary key, and identify all dependencies. This is conversion to first normal form. The dependency diagram depicts all dependencies found within the given table structure, right? So 1NF, all key attributes are defined. There are no repeating groups, and all attributes are dependent on the primary key. Okay. Some table can contain partial dependencies in 1NF, and this would lead to update, insert, and deletion anomalies. So this was the 1NF dependency diagram that we covered, right? We identified the primary key comprises of two attributes, project number and employee number. All other attributes are dependent on the primary key. As we've seen, project number and employee number can determine project name. They can determine employee name, job class, and so on. And then we have identified the less desirable dependencies here at the bottom. Right? This is the first normal form. 2NF, right? And we went through the process. This is a repeat of what we went through. Here's how 2NF looks, right? We broke up the combined 1NF table into three separate tables: the project table, employee table, and the assignment table. So there is still the transitive dependency present, but we don't have any partial dependencies in 2NF. 3NF, we followed the simple two-step procedure where we broke up the transitive dependency into a separate table. So now we have four tables: project, employee, assignment, and job. In 3NF, there are no transitive dependencies, and each table is already in 2NF. Okay. So now, improving database design. Normalization is valuable because it helps eliminate data redundancies, right? And then we can also do a number of other things aside from normalization to improve the database design. Things like evaluate primary key assignments and naming conventions. We look at an example here shortly. We can refine attribute atomicity. So an atomic attribute is one that cannot be further subdivided. An example of a non-atomic attribute is address. The address attribute can be subdivided into, for example, street number, street name, zip code, apartment number, what have you, right? those individual pieces can be considered as atomic attributes, right? Sometimes you can identify new attributes and new relationships. In our most recent example, an employee can have a date of hire. So a date of hire is a new attribute. Sometimes you can also refine the primary keys as required for data granularity. And you can also add fields to maintain historical accuracy and evaluate using derived attributes. So remember, derived attributes are those attributes that are derived from another one. So for example, age can be derived from date of birth, right? And so on. Sometimes you have to assign surrogate keys. In our example, the job table does not have a surrogate primary key, right? In that case, we can use something called a job number as a surrogate primary key. Now, BCNF and 4NF are something we're not going to cover, so we're going to skip these set of slides. So coming to database design and normalization. Well, normalization should be a part of the design process. The proposed entities must meet the required normal form before table structures can be created. So ERDs are created through an iterative process, and normalization focuses on the characteristics of specific entities. So in this example, we're going to go through the same set of tables that we went through, and we're going to see how we can use some of the principles that we just covered in the last couple of slides here. So we have our initial ERD here, right? It's not refined yet. We're going to refine it here. In this ERD, we can see we have two entities, employee and project. Employee has employee number as the primary key and a set of other attributes. Project has project number as the primary key and project name as an attribute. We then created the job table. Now in the job table, earlier we did not have a job code as the primary key. So we create a surrogate primary key called job code. And then we identify the relationship between job and employee. And what is the relationship? Each employee has one main job. A job classification can be held by many employees, right? So a job classification can be held by 0 to many employees. One employee can hold one and only one job classification, right? So notice that some job classifications have not yet been staffed, right? So therefore employee is optional to job. That's why we have this circle here, right? A job needs to be held by 0 to many employees, right? In other words, there can be job codes, descriptions and hours here in the job table that don't have any corresponding records in the employee table, right? Because they have not yet been staffed. Okay, so this is the process of going through and refining the ERD. So let's go to the next step. In the next step, we identify the relation between employee and project. So one employee can work on many projects a project can be worked on by many employees. So the relation between employee and project is actually a many-to-many relationship. And the way we resolve that many-to-many relationship is by the creation of the assignment table, right? The assignment table has assignment number as the primary key, and it has both the project number and the employee number as the foreign keys, right? So one employee can enter into zero to many assignments. A project can relate to one to many assignments. One assignment can be worked on by one and only one employee. One assignment can relate to one and only one project. Okay. So in other words, the assignment table defines what employees are working on what projects. Okay. So here's our implemented database. In other words, this is the database after we created the ERD. We created the tables in the database, and then we entered data into those tables. Okay. Now you'll see here that we added an employee hire date attribute as well. Right, so this is an additional attribute. Also, assign charge is a derived attribute. It is derived from multiplying the assignment hours by the charge per hour. Right, so 2.6 into 8450 gives you this is how much should be charged for that particular assignment. Assignment number 1001. And what does that assignment relate to? It relates to employee number 103 working on project number 15. So employee number 103 working on project number 15. So that's about normalization and database design. Let us now look at denormalization. Now, usually in normalization, as we go up the normal forms, we are decomposing the table to conform with normalization requirements. We're creating more tables, right? So the number of database tables expands as we normalize more and more. However, joining a large number of tables can also put a load on the input-output processing and reduce system speed, right? Joining many tables takes up a lot of memory and so on. So in order to overcome the reductions in performance and to make things easier to look up, right, for a little bit of convenience, we sometimes unnormalize tables, right? Denormalization is usually done by introducing redundancy in the database system. So one particular attribute, for example, might be stored in two different tables. Okay. So here are some common examples of denormalization. Redundant data. So for example, storing zip and city attributes in the same table, even though zip determines city, right? This is always the case that you can determine the city from the zip code. So ideally, you would have a different table that maps zip code to city, but this is almost never done, right? We store both zip code and city in the same table. It could be an agent table or a customer table or an employee table, what have you, right? The rationale is that we avoid extra join operations. Every time you want to find out the city, you would have to join on zip code if you were to store zip and city in a separate table, right? There are also some controls that need to be established, and in this example, a program can validate the city based on the zip code, right? So for example, you could implement a drop-down box. Right. An example of derived data, so storing student hours and student classification when student hours determines student classification. Again, the motivation is to avoid extra join operations, and you can have some controls built in. Right? Like this, there are some other examples here. Right? You can storing the student GPA aggregate value in the student table, when in fact it can be calculated from the enroll and course tables, right? So you can always calculate GPA from all the course grades, the individual course grades, right? But you don't usually do that, right? You store the GPA in the student table, again to avoid extra join operations. And the control is that a program should compute the GPA every time a grade is entered or updated, okay, and so on. Now your textbook has a data modeling checklist. It's quite a useful checklist towards the end of the chapter, and it lists different things that should be done when you are doing data modeling. The first thing to be mindful about is business rules. Business rules should be properly documented and should be verified with the end users. You should ensure that all business rules are written precisely and clearly. There shouldn't be any ambiguity, and they should be simple enough to understand. These rules should help you identify the entities, the attributes that you need to have, the relationships between the entities, and any constraints. Right? We've seen examples of these in earlier chapters. So you should identify the source of all the business rules and ensure that each business rule is justified, dated, and signed off by an approving authority. There are naming conventions that should be followed. The names are typically limited in length, and it is often dependent on the DBMS that you're using. Entity names should be nouns that are familiar to business and should be short and meaningful. They should document any abbreviations, synonyms, or aliases for each entity. Entity names should be unique within the model. And for composite entities, the entity names can include a combination of the abbreviated names of the entities linked through the composite entity. Composite entity is nothing but the entity that is created to resolve a many-to-many relationship, right? By creating two one-to-many relationships. Attribute names should be unique within the entity, should use the entity abbreviation as a prefix. For example, if you have an entity called employee, right, then the attribute names within employee could use EMP as the prefix. So you could have, for example, EMP underscore ID, EMP underscore L name for last name, EMP underscore F name for first name, and so on. Right? The attribute names should be descriptive of the characteristic and should use suffixes such as underscore ID, number, code for the primary key attribute. Attribute names should not be a reserved word. Reserved words are words that are reserved by the DBMS for some specific purpose. Okay. So attribute names should not be the reserved word, because if you type an SQL query, then that reserved word could be misinterpreted, right? Attribute names should also not contain spaces or any special characters such as at and so on. And generally, when it comes to relationship names, these names should be verbs, active or passive verbs that clearly indicate the nature of the relationship. Entities. Now, each entity should represent a single subject, right? Each entity should represent a set of distinguishable entity instances. The entities should be in 3NF or higher. And if you have entities below 3NF, then they should be justified. The granularity of the entity instance should be clearly defined, and the primary key should be clearly defined. Okay. Attributes should be simple and single valued, meaning they should carry atomic data. Attributes should document default values. So sometimes attributes, if no value is entered, they can default to certain values, and that should be documented. Any constraints should be documented. Synonyms of attributes and aliases of attributes should also be documented. Derived attributes should be clearly identified and include the sources of where they are derived from. Attributes should not be redundant unless it is required for transaction accuracy, performance, or maintaining history. Non-key attributes must be fully dependent on the primary key attribute. Relationships should clearly identify the two entities that are involved, the participants, meaning the two entities that are involved in the relationship, should clearly define the participation, the connectivity, and the cardinality, and should document the cardinality. Okay? So again, connectivity was the one-to-many or many-to-many part, and the cardinality is the one or the zero, or the many or the zero part. That's listed in brackets below the relationship at both ends. Okay. The ER model should be validated against expected processes. Will the inserts, updates, and deletions work as expected, as the business processes work? Will inserts, updates, and deletions all be supported by this particular ER model? The ER model should evaluate where, when, and how to maintain a history. It should not contain redundant relationships except if it is required. It should minimize data redundancy to ensure single place updates. single place updates, meaning you should only have to update data if data changes and needs to be updated. You should only have to update it in one place, not in multiple places, right? That could give rise to update anomalies and data inconsistencies. Okay. And ER models should conform to the minimal data rule. All that is needed is there, and all that is there is needed. Okay. So that's it for chapter 6. Do read the chapter. Let me know if you have any questions. Good luck, and I will see you in chapter 7. Thank you.